All right, so in this video, we're going to talk about arc length. And if you remember, I've said it many times, an integral takes a bunch of really, really small things and just adds them all up. So to compute the arc length of, let's say, this curve here we have on the screen, what we're going to do is actually focus in on more of these, what are called lineal elements. And so I'm going to take, let's say, one from here up to here, and then one from here down to here, and then another one from there to there. And you can start to see if I add up all of the lengths of those blue line segments, then I'm getting pretty close to the actual arc length of our curve on A to B. Now it's not going to be exact because I need infinitely many of them, and that's where we're going to let the integral take over. So I'm going to focus in on this middle one right here to help draw our picture. So from here, I'll go ahead and I'm going to drop a perpendicular straight down, and I'm going to come over. Now, we're going to call the actual blue hypotenuse here delta S. A lot of times we use S for arc length, and so this is the one lineal element that we're going to study in particular in this picture. Since this is a perpendicular, we're going to have a delta Y here and a delta X here, and be able now to take advantage of the Pythagorean theorem. So the Pythagorean theorem says that delta S would be the square root of delta X squared plus delta Y squared. So that gives us one of our lengths of our line segments, but we want infinitely many of them. So we're going to now sum up infinitely many of these delta S's. And once again, I'm just going to have this delta X squared plus delta Y squared under that radical. And let's make a note real quick here. We know that delta Y over delta X is going to be the same thing as F prime, which means that delta Y is going to be F prime of X delta X. By making this substitution now, I'm going to replace delta Y with this. Now we're going to be fully dependent upon X and not Y. So now our sum of delta S is going to be the infinite sum, the square root of our delta X squared, followed by our F prime of X delta X squared. And if I simplify this just a little bit, don't really have to do a whole lot to it. You can see here how I have a delta X squared there and a delta X squared there. I can factor that out from underneath, and then the square root is just going to give us the 1 on the outside. So we're going to have now 1 plus F prime of X squared with a delta X on the outside. Now, taking that infinite sum and converting it to an integral, the actual arc length would be the integral from A to B, square root 1 plus dy dx squared dx. Once again, just changing the notation at this point to something a little more familiar to be a little more consistent. And so that's going to be one of our arc length formulas. The other one, of course, we could go with respect to y. I could have completely redone this whole process with respect to y. I don't feel like we need to. We can probably just see that it's going to be the integral from c to d, square root 1 plus dx dy squared with dy. So these are the two formulas now that you have for arc length. Dependent upon the information given, you can make a decision as to which one you want to use. But it's really a very, very simple idea in order to come up with this formula, one that you'll actually use again or see again quite a bit as you move through the calc sequence. All right, so in the example we're going to look at here, we're given x equals this guy here, and we're trying to find the arc length of it from y equals 1 to y equals 2. So these would be the bounds on our integral, and you can see given y equals 1 and y equals 2, and the function is already solved for x, it's going to make sense for us to now go ahead and use the formula where we integrate from c to d, 1 plus dx dy squared dy. Okay, so this one's very clearly pushing us in the direction of using this particular formula. The other thing that I'm going to do before I get started here is I'm going to rewrite the original as x equals 1 over 8 y to the 4th plus 1 over 4 y to the negative 2nd. That's going to help me with the derivative here in a second. So really nothing complicated about this, but it is important to go nice and slow. When it comes to filling this guy out or plugging everything in, I'm a big fan of going step by step. I know I'm going to need dx dy. So my dx dy, which is the derivative of x with respect to y, is going to be a 1/2 y to the third minus 1/2 y to the negative third. Okay? Then in the formula, we have to square it. So I'll come over here and I'll square that. And on the right-hand side, let me write it out so it's going to be easier when we FOIL. So our dx over dy squared. And so I'm going to FOIL this guy out with this guy. So our first would be a 1/4 y to the sixth. The outer would be this guy times this guy, which actually just gives us a negative 1/4. The inner is going to be the same way, negative 1/4. And then the last would be our positive 1/4 y to the negative sixth. So let me go ahead and write that out. Our first was this, our outer, our inner, and our last. And I can now also see that the negative 1/4 and the negative 1/4 can be combined. And I'm going to do that here in a second. But we've got our quantity squared now, so we need to add 1 to it. So I'll take this and add 1. So I'm actually going to go ahead and combine these two things and that in my next step. So that's going to then give us our 1/4 y to the sixth plus 1/2 plus 1/4 y to the negative sixth. Now, you got to remember, I'm about to take this thing right here and place it underneath a radical and still need to be able to actually integrate it. So you'll see in these problems that whoever writes them has to be very, very careful that they allow us in Calc 1 to integrate. So as you see something like this, knowing that it should have a radical over it and I still need to be able to integrate it, something's got to give, right? There's got to be a way that this is going to work itself out. And so when you look at this actually factors. This is going to factor into 1/2 y cubed plus 1/2 y to the negative third squared. And I would encourage you to check that off to the side to convince yourself that it does in fact factor. So then when we actually put it under the radical like we need to, it comes out to where all we're going to have is this 1/2 y cubed plus 1/2 y to the negative third that we need to integrate. So now we'll have our dy here. We know we're going from 1 to 2. So there's our setup now for the arc length of that curve on the interval 1 to 2. So again, you're able to, I guess, if you want to call it cheat a little bit, you know something's got to give when it comes to this. So always remember that in Calc 1, we don't have all of the available integration techniques you will have in let's say, Calc 2. And so they have to be able to give us something that we're able to integrate. And conveniently, this one simplifies quite nicely so that we can just add 1 and divide.